Now let's start today's lecture. So in today's lecture, the main part is about I'll show you some applications using MapReduce. But before that, I realized on Monday. So on Monday's lecture, I have introduced combine by key, which is a fundamental operation and also the basis of many other functions like reduce by key. I have also introduced the efficiency of MapReduce in Spark, what we should be aware or pay attention to when we design a MapReduce program. Then I realized I should mention this as well. So before we start today's main content, which is about the applications, let's see this subtopic in MapReduce in Spark. So basically, it is about how to merge two RDDs. Because in most cases, like we use transformations to convert one RDD into another. This is the most common scenario, but there are some situations that we do need to merge two RDDs. So by merge, there are different meanings of merge or different logic of merge. So so basically there are three types in Spark. So one is union, one is zip, and one is join. So let's look at them one by one. So first of all is union. So union is more or less like you concatenate two RDDs. For example, this is 1 and this is 2. For union, you kind of plus them together, concatenate the second one after the first one. So this is union. Zip is like you pair two RDDs. We all know for one RDD, it is a list of key value pairs. Right. So assume we have another RDD, which is also a set of key value pairs. So by zip, we actually use the elements in the first RDD in RDD1 as key, and to use the elements in RDD2 as value. So what we will have is here let's mark them as this. So what we will have as a result of zip would be a list of RDDs where the element from RDD1 is the key, and the element from RDD2 is the value, and so on and so forth. So this is zip. So for join, you merge based on the keys from two RDDs. So if we look back at union and zip, there's nothing to do with the keys of the element, or we did not do special things for the keys of the element. But for join, the whole process is based on the keys from two RDDs. The concept is just like a join in database, right? So you should have learned this in 9311, right? Okay, so this is how to merge two RDDs. We will explain each and every operations later. But to the best of my knowledge, if you want to split RDD, so if you want to do the splitting, also there are several ways. I mean, at least because there is no, let's say, inverse operation for join, but for union, because union you concatenate two RDDs. So if you want to split them, you can use filter or subtract. Sorry. Right, or subtract. This is for the inverse operation of union. For the inverse operation of zip, to the best of my knowledge, I didn't find one. So if you're gonna do that, you would probably need two maps. Right, so for one map, you kind of take the keys out as a new RDD, and for another map, so this is a map for key and a map for value. So just in case you know what I don't know, and you do know there is if there is a method in PySpark that can achieve this functionality, please let me know and I will add it into the lecture. Okay, so now let's look at all these three operations. First of all is union. So we know that what is union for. So basically you concatenate two RDDs, right? But here what we really care about is how does a union work, right? For example, given A and B, which are two RDDs, how do A and B union together? Or more specifically, what is the number of partitions for the union of A and B? Let's say we have A contains two partitions and B contains another two partitions. So for the operation, we use A union B. Now, what is the number of partitions for the union of A and B? So there are two cases based on the partitioner that A and B are using, right? So for the first case, they are using different partitioner. In this case, the number of partitions of A and B would be the partitions, would be the sum of the number of partitions of A and B, right? So in case 1, it should be like 4 partitions. Yeah, let's say it's A1, A2, and B1, B2. So here would be A1, B1, A2, and B2. Now please note that here the default partitioner is none. So if you print A dot partitioner, you would see that it is none. And if the partitioner of A and B are both none, they will be considered as a different partitioner. So that is kind of a special case here. So that's why if you do not specify the conditioner, even you do A union A, say if A dot partitioner is none, then what you will get is the total number of partitions would be 2 times the number of partitions in A. Okay, because they're considered as different partitioner. Now in the second case, where A and B has the same partitioner, then the number of partitions would be the number of partitions of A. OB, I mean, they should be the same. So you would have something like A1, B1 and A2, B2. So you have A1, B1 in one partition and A2, B2 in another. Right. So this is how do A and B union together. Hope this will give you some initial ideas about the operation here. Right. Now for zip, as we have mentioned before, after you do A zip B, you would get the key value pairs, where the key is the tuples or the elements in A, and the value would be the tuples or elements in B. Right. Now, when we do zip, we do assume that the two RDDs has the same number of partitions and the same number of elements in each partition. So only in this case we can do this kind of one-to-one map. We kind of zip A and B together. Right. So in order to zip A and B, please make sure that not only the number of elements would be the same, the number of partitions would be the same as well. This is for zip. For join, we have 4 different types of join, which are join and 3 other types of outer join. Let's look at join first. So just in case you can't remember the concept, join would produce the all pairs with matching keys from A and B. Now let's assume that A has A1 and B2 as the elements in the RDD, and B has B3 and C4 as B's element. All right. So for join, we would have all pairs with matching keys from A and B. So in our case, the matching keys of A and B is only B here, the small b here. So the result of join would be B 2 and 3. We just concatenate their values to this key as the result of join. So in order to implement that, we do use a hash join across the clusters to finish this join task, as well as the left outer join and right outer join and full outer join. For the details of hash join, just in case you don't know it, I think you can learn it from 9315 database system implementation. That course would give you a better understanding and a full picture of this whole join thing. All right. Now let's look at outer join. So we use a left outer join as an initial example here. So as you can see, there are 3 different cases, right, for the key. For the keys. So the first case is that the key exists in both A and B. right? Just as B here. And the second case is the key exists in A but not B. So that is the A here. And for the third case, the key is in B but not A, so it's C here. So for left outer join, this left means because we are doing A left join B. So left join is kind of something like this. So you kind of merge B into A. So what you care about is the keys in A, but not in the keys in B. So for the first case, it's okay. You would still have a B, 2, 3 here. But for those in A but not in B, you would keep the key. So you would keep A, and you keep the value in A. So in B, there's no key A and no value for A. So you just put a none here. And for those keys that in B but not A, because we don't care about such kind of keys, so you do nothing. You do nothing for C. Right. So the result of left outer join would be like this. And similarly, for right outer join, you kind of do it inversely. So the result is kind of opposite to left outer join, where you would have B 2, 3 and C 9, 4, but you don't have A, right? So for full outer join, you do the union of left outer join and right outer join. So you would have this one, and this one. So you would have all three keys, and you just put a none there if it only exists in A or only exists in B. Now, if you're interested in the number of partitions of the result of these join operations, well, the number of partitions in PySpark is a user-specified parameter. So they will use hash partitions to partition the resulting RDD into the given number of partitions. So that's pretty much for the merge operations of two RDDs. Now let's look at the applications. So the first application is term co-occurrence computation. So what is term co-occurrence computation? Basically, what we want to have is a term co-occurrence matrix for a text collection. So the input would a collection of documents or sentences, and the output is a n times n matrix, and n is the vocabulary size. So for each element in the matrix, so for example, the cell or the element in the ith row and jth column represents the number of times that the ith and jth term co-occur in some context. For example, let's say if we take the terms as the characters here, so this two, sorry, let me see, you probably should, yeah, you will still have this one. Yeah, so this two means that A and A co-occur in some context for 2 times. And this 3 means A and B co-occur in some context for 3 times. And usually this matrix is symmetric, so here would be also be 3, but it totally depends on your definition of co-occurrency, right? Now, why we need MapReduce on this application, or let's say what is the difficulties of this application such that we would need to use MapReduce. Now, there are 2 difficulties, right? The first one is the large event space, means the large number of terms. This makes this makes your output, which is an n times n matrix, would be extremely large. And the second one is a large number of observations, or the collection itself. So this is your input. Yeah, so this is your output, would be n times n. And for your input, you also have a large number of observations. So basically, you cannot process such kind of large input in a single machine. And it is also difficult for you to process such kind of input and store the intermediate result and to get the final result, which is n times n matrix. Right? So that's why we need MapReduce, because MapReduce can process such kind of input or collection of documents parallelly, right? And for the application of term co-occurrence computation, this topic is widely used and researched in like data mining or language model, information retrieval, or bioinformatics, such kind of research areas. Right. So for applications of this term occurrence computation in language model and information retrieval, I refer you to the course of 6714. So this course is information retrieval and web search. It will introduce these applications as well as those concepts and methodologies in detail. So here we only focus on how to compute the term co-occurrence use MapReduce. So the naive solution of this problem is to map a sentence into pairs of terms with its count. So it's pretty much like the word count the word count problem that we have discussed before. Right. So for map, you got a pair of terms, because what we want is the co-occurrence of a term. So you got term 1 and term 2 and with its count. So yeah, this is the key and the count would be 1, right? So for map, you output such kind of information, right? Then you will generate all co-occurring term pairs. Now, if we look at the pseudocode, it would be for all term U in sentence S or in document. It doesn't matter too much. You do the following: for all term V in the neighbors of U, you emit U, V, and 1 as the output for the map. So here the neighbors is defined by the user. Right, so it could be like the keywords before U. Right. For example, U is here. The the sentence is here. So it could be all the terms that appears in this range, right? It also could be, say, all the terms in this whole sentence, or even all the terms in the document. So it is defined by the user. All right. So for the reduce part, we reduce by the key, which is the term pair, and we sum up the counts, just like a word count. Right. So for example, given the sentence, a boy can do everything for girl, what you will generate if we see yeah, let's define the neighbors as the three closest terms to the term u. Okay, so it would be a boy for 1 and a can for 1 and a do for 1 as well. And you would also have for boy, let me use a b to make it easier. So you would have BC, BD, BE, and BA as well. So they will all be, the count will all be 1. And you will definitely have C, D, E, F, G. For each of them, you would have at least 3. At least 3, at most 6. You would have 3 to 6 pairs, where the key is the pairs of terms, and the value is 1. In this sentence, if you don't do in-mapper combiner, right? So then in the reduce part, it gather all the pairs from different sentences or from different partitions and sum up the group by the keys and sum up them together, get the final counts for each and every pair. So this is the naive solution. So the good thing of using this pair idea is that it is easy to implement and easy to understand. As I said, it is just a slightly complex, more complex version of word count, right? But the disadvantage here is that it involves a lot of pair to sort and shuffle around. For example, only for one sentence, we would have at most s times s, the length of the sentence to the power of 2. We would have this much pairs, right, to sort and shuffle. And also, there's not many opportunities for combiners to work, or in the Spark context, you don't have you have not many opportunities to merge these key value pairs together to increase the number of counts before you do the shuffle and sort. So you kind of increase the overhead of sort and shuffle. This is because, as in common sense, I mean, in a sentence, usually the words are quite different. So you would see different term pairs, and you would see usually you would not able to see many duplicates or the same pair of terms in this term co-occurrence situation in one sentence or in one document. So this motivates us to have this alternative solution, which is to use stripes. here the stripes this concept is similar to some extent to the one that we have introduced in erasure coding, but they're not exactly the same, or we could say they're quite different. All right. So basically, the motivation is, or the observation is, the n times n matrix is quite sparse. Sparse means in a matrix, you would see a lot of zeros. The reason is straightforward, right? You cannot expect to see a relationship between every pair of words or terms, right? Now the idea is, previously we record each pair of terms and do the counting, right, for each pair of terms. So for each pair of terms, we would have a key value pair in the RDD. Now, instead of that, for each term, we would use a stripe or a hash map to store the number of co-occurrence between that term, for example, A here, and all the other terms. In this case, for example, here, let's say this is the key value pairs in one partition. Instead of storing 3 key value pairs, we use one key value pairs where the key is the term A and the value is a hash map here. So in the hash map, we would have, because a hash map, you also have a key and value. Sorry. So the key would be the term, and the value is the co-occurrer to A. So you would have 1 for B, 5 for D, and 3 for E. And you can do the same thing for all the partitions. Now, here we just use A as an example, but you can expect in this partition you would also have a B and C, and B and C here as well. Now, how you merge them together? Right. In order to do that, you simply merge the hash map together, or dictionary together. So you just sum up the count as what you have done before, right? So this is what you have. For this 2, you just sum 1 and 1, and you copy this 2 here. You sum 2 and 5, you get 7, and so on and so forth. Now, in order to do it in MapReduce, for the map, well, we map a sentence into a stripe, right? The input is a sentence, and the output is here would be stripes, not a stripe. Right. So in order to do that, for all term U in sentence S, we build a new dictionary for U at first, and then for all terms V in the neighbors of U, we add 1 to the current value of each U of V. Right. So it is easy to understand. Right. And for the reduce part, we reduce by key, which is V. Sorry, yeah, because here what we're gonna emit is U and HU. Right. So we reduce by key, which is term, and we merge the list or the dictionary. here we just use element-wise sum of dictionaries. Well, I'm not sure whether you will ask this or not, but as you can see, for each dictionary it is again a list of key value pairs. So can we put them in an RDD? Well, you cannot. Right. So basically, you cannot build an RDD of RDDs. This is because RDD is not iterable. Therefore, it cannot be parallelizing. So if you're gonna implement this, you will have to do this element-wise sum of dictionaries, not using MapReduce, right? So for this operation, you do it by yourself, not using MapReduce. So it also means, more importantly, this element-wise sum of dictionaries has to be done in memory with no parallel. So that's why we can do it in this way, because we have mentioned here. So there is a lot of zeros in the matrix. So you can expect this dictionary will be not too long. All right. So this is how you do MapReduce on using this stripe idea. Now, the advantage of this stripes idea is that there are far less sorting and shuffling of key value pairs. Say before it is S times S, and now it reduced to V, and this V is the vocabulary in S. So it is so the number of key value pairs is much less, and hence the sorting and the shuffles will be much less as well. So the disadvantage of this stripes idea is that it is more difficult to implement obviously, and the underlying object is more heavyweight. Previously, it is just a number, right? Or say a count, which is an integer. And now it becomes a hash map or a dictionary, right? And the third thing is that there is a fundamental limitation in terms of size of event space, which is the number of terms. That is to say that you have to fit the total strip in memory in order to do this reducing to sum up them together. So yeah, it is limited by the size of the event space, but thanks to the sparse property of this matrix, so in most cases, we can do this in using this stripes idea. Right. But again, it is a disadvantage. Now, if we compare this pairs idea and the stripes idea, the pairs approach keeps track of each pair of co-occur terms separately, right? And the stripe approach keeps track of all items that co-occur with the same term. And the pairs approach generates a large number of key value pairs. These are also the intermediate result. The stripe approach generates much fewer and shorten intermediate keys. In this case, the framework has less sorting to do. Right. The pairs approach benefit from the benefit from combiners is limited because it is unlikely for a mapper to process multiple co-occurrence of a pair of words. So there is not many key value pairs to be combined together. But for the stripe approach, it greatly benefits from combiners as the key space is the vocabulary. So you would expect to see a lot of key value pairs with the same key in that partition, so that you can combine the values first, before do the reduce thing. And more and the stripe approach is more efficient compared to the pair approach, but it may suffer from the memory problem. But for pairs approach, as long as the memory can, so for the pairs approach, this won't be an issue. Right. Now let's look at the second application, which is building an inverted index. Now, while search engine is nowadays like the service that you use every day in real world, right? So in this example, we would see how MapReduce could help to build a search engine. All right. So first of all, we have to introduce some concepts here. So basically, this whole thing is related to information retrieval. And here we only focus on the textual information, which are text or documents, right? And the retrieval of these objects. And there are other possibilities, include image or video or music. In that case, the general idea is to convert them into vectors, high dimensional vectors, and then you can perform retrieval on top of that. So interestingly, we are going to introduce this from next week because the high dimensional vectors and the search operation based on in this high dimensional space is also an important concept in big data. All right. Now let's come back and look at the textual information retrieval. Well, the easiest and fundamental model or method is a Boolean text retrieval. So in this case, each document and the query is treated as a bag of words or terms, and the word sequence is not considered. I mean, so here the word sequence means the order of the words is not considered. So each document would be converted into like W1 and W2 to Wn, where n is the total number of terms or words in the document. Now the query terms are combined logically using the Boolean operations like and, or, and not. For example, here the query is a data and mining and not text, right? So which means this query wants to find out those documents that have both data and mining, but with not or does not have without or does not have text, the word text. So in order to do the retrieval, the naive idea, right? Given a Boolean query, the system retrieves every document that and to see whether it makes the query logically true or not. So it is an exact match, right? It is an exact match, and there is no rank. Right, so there is no rank because either it match the requirement of the query or not. Now, in order to speed up the retrieval process, here we use the data structure called inverted index to help do the retrieval. The inverted index of a document, of a document collection, is a data structure that attaches each distinctive term with a list of all documents that contains the term. All right, so it is an index. So for index, it must have a key and value, right? Well, look familiar, right? Because we have key and value again, right? So we will discuss how to use MapReduce to generate or to construct the inverted index. So the key would be the term, right? So the key would be the term, and the value is a list of all documents that contains the term. So the value is a list of documents, right? Contains the term. And the documents containing a term are sorted in the list. So there are several reasons we do this sorting. First of all, this sorting would help the query processing, which we would see later. Right? And another reason is that this sorting enables us to perform data compression on the list of documents on this list. So we won't dive into that topic in this course. But again, I mean, these are covered in the information retrieval and web search course. So this course is available next trimester. So if you are interested, you can enroll that course. Right. Okay. Now, for the retrieval, it takes a constant time to find the documents that contains a query term, right? Because it is just need to look up in the dictionary or in the index based on the key, which is the term, right? So it's a O1 operation, and the multiple query terms. By multiple query terms, we say, for example, data, mining, and text. There are 3 query terms. So we have we take constant time to find the documents that contains one query term, and for multiple query terms are also easy to handle, as we would do something like merge the lists. Now this is an example of inverted index. Right? Assume we have documents 1, 2, 3, and 4. Right? So, and for each of them, we just have some terms in each and every document. For example, the blue, right? Blue appears here only. So as you can see, if we use a matrix to record, say this is whether blue appears in document 1 or not, and it appears in 2 or not, 3 and 4, so on and so forth. So for blue, it only appears in 2. And for example, our fish, it appears in 1 and 2, in document 1 and 2. So we will see 1 and 2. Here the cell is filled by 1. By 1. Right. So this is not an inverted index. This is the inverted index. So in order to build the inverted index, again, the key is the terms. and the value is a list. Right? A list of document IDs. So here, for all the terms except fish, because they only appears in one document, so the list has the length of 1. And for fish, as you can see, there are 2 elements in the list of fish, which are 1 and 2. So the elements here are the document ID, which is from 1 to 4, as you can see. So this is what an inverted index looks like. We will probably stop here, have a break, and we will come back later to see the query processing using inverted index, and then we will discuss how to use MapReduce to generate or construct the inverted index.